Good afternoon. So I was told, I was emailed that I forgot to do two examples. Well, I did, but it's not that my old computer was overheating. So I'm back to go over example number 4 and example number 5. I'll make myself smaller so we can go through this. So in this case, it says let A and B be real numbers, so they cannot be imaginary, they cannot be complex, such that A is less than B. P, if P is a polynomial function such that P of A is not equal to P of B, so therefore whenever you plug in the A and the B, they're not going to be the same value. Then in the interval A, B, including the values of A and B, F takes on every value between P of A and P of B. And if you guys remember, that makes sense, right? Because polynomial functions are continuous, there are no gaps, and they continue beyond. So therefore, if there's a function, then there's going to be every value inside the function. So if we take a look briefly at Desmos, so let's go and type that one up. So we're going to Desmos, and I'm going to type, click on graphing calculator, and I'll type in the function. The function that we have is f of x, and you can type in f of x or y equals. I prefer to type in f of x. So I'll type in f of x equals x to the power of 3 minus 2x to the power of 2 minus x, and I always make sure that I click to the right so I can do the exponents a little faster, plus 1. So notice that in this case, this graph is continuous. Do you agree? So therefore, every single value that you plug in is going to exist. So if we say that in this case, f of 2 and f of 2 and f of 3. So let's go and type in f of 2 and f of 3. We're just going to click on the next line, and that'll give us f of 2 will give us -1. And in this case, let me make myself a bit smaller. That might be helpful. So therefore, that will allow us to plug in a point, which is, remember, f of 2, so as your x is 2, y is -1 according to this. And if you want, we can do it manually. But in this case, Desmos does it for us, which is very, very, very helpful. So now, let me bring myself up here. We can type in the next point. The next point according to this is f of 3. And if we evaluate, that will give us a 7. So therefore, if you plug in a 3, it gives us a 7. So that means that for every single point, there exists a value at any, if you plug in a 2.1, it's going to give you a value, 2.2, 2.3, 2.4. Any value all the way up to 3 in that section is going to give you a value. So that's basically what the intermediate value theorem tells you. It tells you that throughout the interval, there exists a value at every single point in between, including A and B. That makes sense, right? According to a graph, if there exists a value, since it's continuous, that's going to be always the case. Now, the important part is this section here. If the values of P of A and P of B are opposite in sign, one positive, one negative, then there exists at least one real zero between A and B. Now remember, what are real zeros? So in this case, if we actually look at the graph, if that's the y value is -1, and on this one, the y value is +7. So if they have different signs, and because it's continuous, what does that mean? That means that there has to be, it has to cross the x-axis at one point, right? If you have a point here and a point here. To get from one to another, you have to go through the x-axis. So that's pretty logical. That makes total sense. Do you agree? So now we need to be able to show that algebraically. So let's go through the process. Let's show algebraically that we can actually do so. So first we need to be able to show that the polynomial function has a real zero between 2 and 3. That means that we have to plug in a 2. So therefore, if we plug in f of 2, and if we plug in f of 3, if there exists one real zero between them, then one negative, one positive, and the 0 will be in between. So let's try f of 2. So that'll be x to the third power minus 2x squared minus x plus 1. And instead of the x, I'm going to replace it with a 2. And we have 8. That gives us 4 times negative 2 will give me negative 8 minus 2 plus 1. So that's 0. Negative 2 plus 1 is negative 1. Just like we saw in decimals. So therefore, the point is 2, negative 1. You have to keep that in mind that that is a point. So whenever you see this notation, it corresponds to a specific point on the graph. Now let's do the second one. For the second one, we're going to go through exactly the same process. So go and pause it, find f of 3 algebraically, and see what you get. Got it? So in this case, this will be x to the third minus 2x squared minus x plus 1. But instead of x, now I'm going to plug in a 3. Everybody knows that 3 to the third power is 27. That gives me 9 times negative 2 is negative 18 minus 3 plus 1. So that gives me 9. That gives me negative 2. Therefore, that gives me 7. And remember that this corresponds to a point. So the point is 3, 7. So therefore, there exists a 0, a real 0, correct? Because on the next section, we're going to be talking about imaginary and complex solutions. In this case, there exists a real 0 between 2 and 3. Why? Because we end up with two types of solutions. Why? Because you'll give a, if you plug in a 2, gives us negative 1. And if you plug in a 3 gives us a 7. So 1 negative and 1 positive. And if we look at our graph, we can actually find the value. So let's see, what is the value? Let me see if I can. So what is the value that we get? So let's go find the exact value. Notice that in this case, that's one of the zeros, but the 1 0 that we're looking for between 2 and 3 is 2.247. And let's say the 0 is, let me just move this to the left. So therefore, we can see above the 0, the real 0 is x equal 2.247. 2.247. Now let's do it on the graphing calculator, because I know that all of you guys have a graphing calculator. So on this one, it's very easy because you can just click there and it's there for you. But now let's go and do it on the graphing calculator. On the graphing calculator, we have, let's go in Y. I'm going to clear that up. Now, if you see the plot on top, you want to be able to clear that up as well. So I'll go over to the top, press enter, go down, and type in the equation of x to the power of 3 minus 2 x to the power of 2 minus x plus 1. And now I want to go under zoom, and I'll go under standards. Now it takes a bit of a while. Sometimes it takes a little while for it to think. I'll go under zoom. I'm going to standard, and then that should be able to show me the same graph that I have, correct? Now to actually find the zeros, what I'm going to do, I'm going to calculate. It's in blue, so second, calculate. I want to calculate the 0, which is the number 2. I'll come down, press enter. And now it says to find the left bound. So therefore I need to be able to find any value around here. Actually, I'm going to go down above, a little higher, a little lower, somewhere to the left. And notice that it does show you guys a little line if you have the TI-84 plus CE. If you have a regular TI-84 plus, it doesn't. Then I'm going to go above, and then I'm going to press enter. And then it says, do you want me to guess? You're going to say, yes, I do want you to guess somewhere in between. And that should give you the same value, which is here. That's how you do on the graphing calculator. So let's go to example, last example that I skipped. Example number 5. So in example number 5, we have the following. We have the remainder theorem that says if a polynomial p of x is divided by x minus k, the remainder is the r is equal to p of k. That means that if you plug in the value of k, that will give you the remainder. So we're going to do it two ways. We're going to use the syntactic division or syntactic substitution and direct substitution to be able to find the remainder, which is as if we were evaluating the function. So therefore, am I missing any zeros? For x to the third, x squared, x, and then the number? No. So therefore, I can just place my L, which is 4, 10, -3, and -8. Outside will be x equal to -1. Now, remember that in this case, they're talking about a factor, but we can actually go back and if you move the 1 to the left, so x equals -1, move the 1 to the left, you end up with x plus 1 equal to 0. So therefore, this will be the factor. Correct? So therefore, we're going to plug in a -1, and then we'll start the process. 0. You add, you multiply. -1 times 4 is -4. Then we add, gives us 6. You multiply. -1 times 6 is -6. Then we add, gives me -9. -1 times +9, we add, and that is a remainder. And that's what we learned, that was a remainder, correct? Well, according to this, this is also, if you plug in F1, this is me plugging in a -1, according to this, that will give us a 1. That is what the theorem is telling us. So let's confirm it. Let's plug in a -1. And according to this, should give us a 1. So it'll be 4x to the third plus 10x squared minus 3x minus 8. And I'm going to plug in a 1. 1 to the third power is 1 times 4 is 4. 1 squared is 1 times 10 is +10. That gives me a -3. That gives me a -8. That gives me 14 minus 11. What happened? Diaz, you're supposed to plug in a -1. According to this theorem, it's supposed to be true. So that gives me -1 to the third power is -1 times 4 is -4. -1 squared is +1 times 10 is 10. This gives me a +3, and that gives me -8. So therefore, that gives me 6 minus 5 will give me a, so that gives me 6 minus 5 is equal to 1. So therefore, if you do not make any errors, that should confirm your value. And remember that should also tell you that if you plug in a -1 into the function, so therefore, if I just quickly go into decimals, and let me just delete everything that I have in here. Therefore, if you plug in everything into decimals, and we have 4x to the power of 3 plus 10x to the power of 2 minus 3x minus 8. Then, if I plug in, that's the function. If I plug in a negative 1, that corresponds to a point, and that's negative 1 comma 1. But now we are able to find the same answer using synthetic division, which might be a little faster than regular, not synthetic division, synthetic division to find the substitution, right? We call this synthetic substitution as well, rather than direct substitution. But all three concepts are the same, which means that if you plug in a negative 1, you end up with a 1. So I apologize for my computer being too slow. Have a great day, and I'll see you guys next time.